Congratulations for making it to the last podium presentation. A quick programming note. My presentation here is going to be a little more general than the paper in the proceedings, and so the title is different. I'm going to be talking about a 3D Parylene sheath electrode. A 3D Parylene sheath electrode is a neural electrode specifically designed to measure single unit action potentials chronically. And the reason why you want to measure single unit action potentials over the long term is because it can advance basic neuroscience research if you know what the neurons are doing over long periods of time. Also, it can help lead to advances in existing neural prosthetics. For example, creating a closed-loop DBS system to better take care of diseases like Parkinson's and epilepsies. And one of the most exciting areas of research for measuring single unit action potentials is in motor prosthesis. If you think about your hand, it does a lot of interesting things. It goes backwards and forwards and left and right. Not to mention that you have a hand on the end of it that can open and close and rotate. And so for all of those different modalities, you need another degree of freedom. And the more individual neurons you can record from, the more opportunities you have to add degrees of freedom to the neural prosthetic. Now I brought a video, this is from one of my favorite shows, 60 Minutes, and they implanted an electrode that's measuring neurons inside of her brain. And this is about 5 months after the implantation. They gave her time to train with the equipment and to heal from the surgery. And then we're going to see what she's able to do with the prosthetic arm. Okay, so here they are connecting her to the computer, which the electrodes are connected to her brain. And then she demonstrates what she's able to do with this prosthetic hand. She can raise it up, and she can go back and forth and up and down. Notice how astonished Scalpelli is watching it. And then when he says it's the most astounding thing he's ever seen, and when he sees that she can open and close her hands, he asks if they can shake hands, and she says they can. So he goes over, he shakes her hand, and he has like this religious experience as he grasps her hands. He says, "Oh my goodness." and then what she does, she gives him a fist bump. And he says, "Oh, no." And he's like, "That's so amazing." Anyway, it is quite an amazing system. A paralyzed woman that can't move her arms and legs is moving a prosthetic arm just as if it were her natural arm. And as an engineer, you would look at this and you said, and you might think, as engineers do, that there's a lot of places where the system can fail. You have a computer with complex algorithms, you have a highly complex robotic arm, but it might surprise you that one of the most difficult things to design is the connection that the microwires have to the brain. And that's difficult because of the design of the microwires. Microwires in the brain, they can range from very simple to complex. So the most simple form of microwire, you just take a group of microwires together, you de-insulate the tip, you bring them together, put a little dot of epoxy and let it dry out, and that's your microwire array. They can get a little more complex. You can do the same thing out of silicon. So you take a really thick silicon wafer, you cut out the spikes, and then you put a conductive tip on them. And so each spike has one conductive tip. Or you can get really complex and take a thin silicon wafer. You can pattern microelectrodes down the length of the shank, and then you can etch away at the shank, and then you can glue a whole bunch of these shanks together to make an array of these microelectrodes. Now, these microelectrodes aren't used that much in people today because they don't last very long. And so right now, the only one that has FDA approval even for clinical investigation to see if they can be used chronically in humans is the Utah ray. And the reason for this, some of it was covered in the previous talk. Picture. I'm missing a picture here. But what happens is when you insert a microelectrode into the brain, you have an aggressive immune response, sort of what was talked about earlier. You have the macrophages in the brain, which are microglia. They're attacking the electrode, and they gather around the electrode and create a scar around the electrode. And you also also have the microglia releasing cytokines, which is telling the neurons to pull away from the microelectrode. So you get this double whammy effect where the neurons that you're trying to record from are moving farther away from the microelectrode, as well as you're getting a scar around the electrode, which is raising the impedance, making it more difficult to record from the electrode. And what this does to the signal quality, if you look at just the schematic of what happens, the signal quality can be defined as the signal-to-noise ratio, or the ability to get signals from the neuron, or to measure action potentials, is that over an acute study during the day of the implantation, you get nice recordings, but then immediately you get a drop in signal, and then it takes about 14 days to recover. And then you get a nice chronic phase that lasts for about 1 year to 18 months. But then the degradation rate increases and eventually the electrode will fail. Now, if you were to make a better design of electrode, you can increase the length of the chronic period as well as improve the signal during this time. And ultimately, the goal is to eliminate this failure period if that's at all possible. One interesting design of a microelectrode was done by a neurosurgeon who used some of the materials that he had in hand. He took a patch clapping micropipette, so one of those really tiny pipettes that you make out of glass by pulling them. He took the very tiny tip of that, broke it off, put microelectrode wires on there, put some neurotrophins in there to encourage neurons to grow into the cone, and put that into someone's brain. And he got pretty good results. He was able to stimulate growth into the cone, and he was able to successfully record from single units for over 7 years, or it was about 6 years, and then he had some reversal surgery and raced into 7 years. Now, as good as this design is, it does have some limitations. One of the main limitations is it's a very small tip, so you can't fit that many microwires in it in the first place. The other thing is it's made by hand, so this slows down, it limits the amount that you can produce, and also each one is going to be a little different from the one before. And also it is very rigid because it is made from glass, which we've had some earthquakes lately, and you notice like the water mains going to the houses. If you have the house moving and the water main not moving, then it can break. And so if you have a lot of neurons inside of this glass thing and the brain is moving, which it does as your heart beats, the brain pulses. If that's moving around, it could rip some of the neurons or cause some damage to the surrounding tissue. So that is where the Parylene sheath electrode comes into play. The Parylene sheath electrode is designed to maintain all the positive qualities of the neurotrophic electrode and trying to reduce as many of the limitations as possible. And now how the Parylene sheath electrode is made, we use micromachining. So we start out with a silicon wafer, we deposit Parylene on it, and then we pattern platinum electrodes on top of the Parylene, and then we deposit the Parylene sheath on top of that, and then we etch out around the probe, and then we can peel the Parylene off of the silicon. And so the final design does not contain any silicon, it's peeled off, and it's just made completely out of Parylene and platinum, which have a good track record of being biocompatible. And so what this allows us to do is to have a customizable design that allows it to be precisely manufactured, and it allows us to create the same probe each time. We can make a whole batch, a whole wafer of these probes at once, so they're mass producible. And they're made from Parylene, which is flexible. It's still much stiffer than brain tissue, but at least as the brain pulses, it will move along with the brain. What I didn't tell you is the neurotrophic part of the neurotrophic electrode. What Phil Kennedy did, he was the neurosurgeon. He first used the sciatic nerve. So peripheral nerves are known for their ability to regenerate. And so during the surgery, he would actually excise a portion of the sciatic nerve and then thread that through his little cone here, and then the neurons would grow into it. Later, he didn't like doing the surgery. It's understandably complex and difficult to do. And so he used commercially available products. He used Matrigel, which is a commercially available extracellular matrix, and he also used commercially available nerve growth factor. For the Parylene sheath electrode, and this allowed him to get ingrowth into the cone. This is an explanted cone, and it shows that there's cells growing inside. And he attributes the success of his cone to the ingrowth of cells into the cone. For the Parylene sheath electrode, I wanted to use the same materials that Kennedy started out with, using Matrigel as a surface for the neurons to grow onto, and then as NGF as a means to support the neuronal survival rate. I also wanted to add on to Kennedy's methods by using BDNF, a brain-derived nerve growth factor that's known for increasing new growth of neurons and to increase sprouting of the dendrites from the neurons. And I also wanted to use dexamethasone to hopefully mitigate some of the immune response, reduce the number of microglia that are attacking with the electrode. I particularly ran into some troubles that Kennedy didn't have. Kennedy's probe is made out of glass, which is much more hydrophilic than Parylene. So when I tried to dip our Parylene sheath into major gel, it's a liquid at 4 degrees Celsius. I got a huge bubble, and then I just pulled it off, and all of the major gel sort of beaded off the Parylene. So my first idea was, when I put it in the major gel, to put it to sonicate it, and the sonication breaks the surface tension across the bubble and pulls the major gel into the sheath with the following result. This is the uncoated electrode, and this is the coated probe. And as you can see, there's a line around it where you can see where the major gel was able to stick to the cone. And if you zoom in on the electrode, you can see that the electrodes are nicely coated. And also, you probably can't see, but I can see, you can almost see here. You see that there is major gel that's actually going down inside the cone that will hopefully drag some neurons down into. As good as this was, I didn't like that it was not uniform. It didn't. There was a different thickness along the edge. So I came up with a surface modification method. I soaked the Parylene in order to increase the surface energy of the Parylene. I soaked it in poly-D-lysine. And what that is it's a polycationic molecule, so it puts a lot of positive charges on the Parylene, and water loves positive charges. So then when I put a drop of major gel on top of the Parylene sheath, the major gel was able to be pulled into the sheath. And then I dried it out with the following result. You can see it's nice and evenly coated. This is a later version where we incorporated perforations into the probe. All those perforations are filled, and it's nice. The major gel goes all the way out to the edges, and it looks quite uniform. Now, my favorite part of it is there's this nice trail of thick major gel leading down into the cone. It's sort of like leading breadcrumbs, or it's like a highway down to the middle of the cone. So if you look at them side by side, you can see that there's some unevenness in the sonication method, but the surface modification method is nice and uniform. So my next task was to figure out how much drug I could load into this major gel. I was using the major gel also as a drug carrier. I started with Dex because Dex absorbs light at 242 nanometers, so I can use it in spectrophotometry to measure it directly. So this is a graph of the more Dex you have in solution. This is just Dex in saline. And the more Dex you have, the higher the absorbance is. And so what I did was I took probes that were coated using the sonication method and the surface modification method, and I put them in a microwell with saline in it for an extended period of time, pulled the probes out and measured the absorbance, and this was the result I got. The surface modification method is the dashed line, and the sonication method is the solid line. And the dashed line is much higher, meaning that I released a lot more Dex when I used the surface modification method than when I used the sonication method. Next, I wanted to see sort of the time course release. So instead of just putting the probe in the microwell with saline over a long period of time, I put it in the microwell, took it out, measured the absorbance, put the probe back into the microwell, pulled it out, measured it again for different time periods. And the result was that the absorbance increased during the first time period, but then leveled off. And so that was after just 15 minutes before a half hour. And then I repeated this study, except with NGF and BDNF, and I couldn't do the same thing measuring the absorbance directly because NGF and BDNF are proteins, and they both absorb light at 280 nanometers, so I had to use ELISA kits, antibodies to get the absorbance of the NGF and BDNF. And I used the coupon instead of the probe. But my results were that the NGF lasted about 6 hours, and then the BDNF lasted somewhere between 6 hours and 20 hours. So the takeaway message is all my drugs are being released in about an hour, but the NGF and the BDNF lasted longer, and this makes sense because NGF and BDNF are about 200 times bigger than the Dex molecule, and so it takes longer to get out of the NGF. We also did an in vivo acute study, and this was in preparation for a more chronic study. We wanted to see, now that we have the probe, does it actually measure signals? And so we did an in vivo study to measure, or to develop an implantation method We tested 3 probe designs, which further emphasize the customizability of our design. We have a sharp taper, moderate taper, and a blunt cylinder. And I was also able to test different conditions to see if these neurotrophins I was putting in or the DEX I was putting in was actually making a difference compared to just using the nature gel. The results of the study were, we did get signals. So during the first day, we had that period of time where we weren't able to get signals. And then after about 14 days, we measured signals again, and we're getting robust signals. The results of the histology for the different designs were that the sharp taper had a much better reaction. Right here, the dark areas are astrocytes and the red areas are neurons. So the dark areas are the least on the sharp taper. And also, this is a good response even compared to the other type designs of microelectrodes that I showed earlier. Also, in terms of the coating, we found that the dexamethasone and the neurotrophins increase the probability of measuring an event rate, which is the action potential, compared to the nature gel by itself. So, in conclusion, our lab designed and fabricated 3D Parylene-based microelectrodes, and I developed a method and improved it for coating the Parylene sheath electrodes with drug-loaded nature gel. We completed an in vivo study, and we have a chronic in vivo study ongoing. Some of the probes have been measuring action potentials for up to 9 months, so it looks encouraging. And so most importantly, we demonstrated the potential of using Parylene-based microelectrodes to measure chronically measure neural recordings. And I'd like to thank my funding sources and my lab, my advisor, and our surgeon, and the manager of the clean room. Couldn't do it without them. And thank you.